All right, folks, so I'm going to talk to you about the observed phase dependence of ejector particles in the DART impact plume using LiSECube's Luke imager and using this analysis to estimate some low limits to the mass observed in the Luke field of view. Next slide, please. The double asteroid redirection test mission impacted the moon dimorphos of the Didymus binary and successfully demonstrated the kinetic impactor technique. Observations of plume brightness due to scattered sunlight from the ride-along companion CubeSat LiSECube of the spatial structure and temporal evolution of the ejector plume are being used to help determine the full 3D vector momentum transfer and constrain physical properties of the asteroid, such as strength and porosity. Optical scattering properties of the ejector particles dictate the relation between observed brightness and inferred ejector mass. So we would like to know what is the characteristic size of slower high mass particles in the plume. This is because the smaller, faster ejectical particles are likely to be outside of the field of view in the LiSECube Luke measurements and may not contribute as much mass as the larger particles. So for this study, we examined plume brightness as a function of phase angle to help identify a characteristic ejector particle size. In the observations, we compared these changes in brightness with radiative transfer forward models using variable plume mass, utilizing scattering phase functions, including those from our previous work in Lolachi et al. 2023. Our phase functions are a series of scattering models for impact plume ejector fragments based on plausible real-world analogs, many using laboratory measurements from the works of Munonan et al. And some others. From our observations versus model phase function comparison, we can establish a characteristic particle size. This is because large particles have a phase function that gets dimmer with increasing phase angle, and smaller particles have a phase function that gets brighter with increasing phase angle. If one assumes a power law size distribution, you can then calculate a low limit field of view plume mass estimate. Why is this a low limit? Well, because for this work, we assume the plume is optically thin, but in reality, at least the inner portion of the ejector plume seems to be optically thick, means there's probably more mass hiding in there that we have not accounted for. Results from our analysis show that plume brightness decreases steeply with phase angle, so this indicates large grains are dominating the observable light. And assuming a power law size distribution, we estimate a lower limit field of view plume mass somewhere to be in the region of 0.6 to 1.2 times 10 to the 7 kilos. So that's the quick overview. So now we're going to go into a bit more detail. Next slide, please. So here's the pointing geometry of LiSECube as it flew past the ejector cone created by the DART impact. In this figure, DART and LiSECube are flying from right to left. The key quantity here is that of phase angle, alpha, the angle between the incoming sunlight, the yellow arrows, and the LiSECube line of sight, the blue arrows at the plume surface. You can see the full 3D geometry on the left and a simplified form on the right. Next slide, please. So we have to do a bit of data reduction. So this is a quick overview slide. Now, there's some issues with the data set from the Luke imager in that it's not fully calibrated. And so we have a responsivity number that we need to turn into radiances. So I'll go a little bit into all that now. So we start off by creating RGB subframes, that 512 by 512 pixels with dimorphos centered. We then basically select images with that meet certain criteria: distance to the target asteroid less than 200 kilometers, no significant clipping, no saturated pixels. Background subtraction is basically done by fitting to points around the target and then fitting those to a background plane to do the background subtraction. And then stray light is basically dealt with by masking Didymos, because that's the main source of stray light. And then to actually work out the responsivity and convert those numbers from the LiSECube data into radiances, we basically use the Pleiades as a calibration source. Next slide, please. So here is basically our family of phase functions acting as analog models for scattering behavior of the ejector particles. A phase function tells you how a particle's brightness on the y-axis changes with the phase angle on the x-axis. There's a lot of curves here, but you can see that they cluster into 3 distinct groupings. These groupings happen to be controlled by the size of the particle, as indicated by the labels on the right-hand side. Next slide, please. So our simulations utilize a collection of phase function models, discrete dipole analysis, and measurements of grain sizes from lab measurements spanning submicron to centimeter scales. So grains of radii less than 300 microns are combined into one category, fines, since their forward scattering shapes are highly correlated and cannot easily be separated by any retrieval method. A systematic change in phase coefficient, in other words, the gradient of these lines, is observed with increasing grain size. So fines exhibit forward scattering, whereas large fragments should exhibit an asteroid-like phase curve. In other words, it goes down. So these analogs can be compared with Luke measurements of plume brightness versus phase to constrain grain size. Next slide, please. So this is basically where we do just that with real data. So this is a set of images in the green channel from Luke with increasing phase angle and measuring brightness, where brightness is indicated by I/F. So you can basically see that as we increase with phase angle, Plume I/F, also brightness in this case, basically goes down. And so that basically indicates that we've got large particles. And although this is for the green channel, we see a similar story in the red and the blue. Next slide, please. So to get mass, then we basically need to start by collecting all the light. So we do that by integrating radially outwards. And we know that we've collected all the light when basically the integration starts to flatten out. So we've got some sample curves on the right that show you that for some of the images. Next slide, please. So once you do that for all of our sample images, you basically end up with this plot that you have on the left here. So this is essentially net plume radiance for each of those images, and then they've been mapped to their corresponding phase angle. So you see that we have two clusters, a low phase angle and a high phase angle cluster. But the thing is then, okay, so now that we've got that, how do we actually turn that into a mass? So the thing is that we have to do a retrieval, but we don't retrieve mass directly. Instead, what we do is we retrieve brightness. So from our three phase curves, we essentially have three size bins of categories like small, medium, and large. And what we can do then is basically have a scale factor for each of those phase functions to say, all right, how much of that phase function is contributing to the total light? And we retrieve that, and that's what Sj is in that equation there. So brightness is on the left, Sj is the scale factor for the phase function, and then you basically work out the best value of Sj for each phase function in each image, and then work that out. So once you've got that, you can then turn that into mass using the equation at the bottom. However, you basically need to assume a power law size distribution and a fragment density. So next slide, please. So that basically gives you this. So these are our retrieved values of Sj. So you can see that we've got an overall decline from small alpha to large alpha, consistent with millimeter grains or larger. However, data shows unexpected trends in the small phase angle and big phase angle, high phase angle clusters. And this is basically likely due to the optical depth problem that I mentioned at the beginning, where the center of the plume is optically thick. Next slide, please. So once you assume a power law size distribution, so P here is the power of that power law, you can basically turn those estimates into masses. And that's what we've got here. So we've got P ranging from 2.1 to 4. And this is based on realistic size distributions from Itakawa et al. And Cheng et al. And so you can see that radiance basically results do show the enormous influence of brightness from the fine grains as well, which are on the order of 10 kilos, but they actually contribute a lot of the brightness. Now, the mass retrievals pick out contributions from the fines and the large grains, but they seem to basically not resolve the millimeter grain contributions in the middle, where, you know, I've got our small size bins, small, medium, and large running around the top. And again, this is probably due to the optical depth problems that we were mentioning. Nevertheless, we're able to get some lower limits, and depending on your size, power law size assumption, you get something between 6 times 10 to the 6 and 1 times 10 to the 7 kilos. Next slide, please. So what have we learned then? Well, we're able to do estimates of plume mass, and when we compare that with observations from others, such as the ALMA observations, we see that our results are consistent. So now their numbers are a bit higher, 0.9 to 5.2 times 10 to the 7, but that's because they can basically see the whole ejector plume, not just the limited field of view that the Luke images saw. Now, obviously, as we mentioned, some of the plume regions appear optically thick, and that means that we can only state lower limits at this stage. So we have a lower limit plume mass present within the Luke field of view that's somewhere in the region of 0.6 to 1.2 times 10 to the minus 7 kilos. So future work is basically looking at simulation codes, migrating that from IDL over to Python and using SPICE to help improve our pointing accuracy, and taking cone geometry into account, and also now including multiple scattering models to basically deal with this problem of optical depth and optical thickness in the center region of the plume. So next, and with that, I'd like to thank you very much for listening.